Okay, so today we will continue with our revision so we can make sure that you have the needed background to proceed forward in this course and to make sure that all of the students are at the same level of knowledge before starting our new syllabus. Um, Today we will continue with AC circuit revision. What we covered so far in AC circuit revision, we covered the waveform and phasor representation, what is the difference between time domain and frequency domain, and how we can go from time to frequency to solve the circuit so we can use complex numbers, and after we finish frequency domain we go back to time domain. And this is the idea of using vectors or phasors because it's hard to deal with AC circuits in time domain because you will have to deal with sine and cosine functions, and you will have to deal with differential equations, which is not easy. If you move to frequency domain, now you have vectors, or you have complex number calculations which you can do easily using your calculator. Then we studied what are the elements in AC circuits, and these elements can be sources like a voltage source or a current source, or this element can be a load, and this load can be resistance, inductance, or capacitance. And we saw how to deal with RL and C in AC circuits, and we said that the resistance in AC circuits is R with angle 0, the inductance in AC circuit will be J omega L in ohm, capacitor in AC circuits will be minus J over omega C in ohm. This is the frequency representation of the elements R, L, and C. And if we are using this frequency representation, we will have all the values in ohm, so we can use just Ohm's law that V equals Z. Z is impedance multiplied by I, and the difference between Z, or the impedance, and resistance or inductance or capacitance, that the impedance has the time information or the time relation between voltage and current, in addition to the magnitude relation between voltage and current. We said that the voltage is a waveform and the current is a waveform, so there is a relation between them in time domain as phase shift, and there is a relation between them in magnitudes. Then we covered how we can apply laws in AC circuits, how we can deal with KCL and KVL, and we mentioned that we will do KCL and KVL in vectors instead of doing it in magnitudes, and Ohm's law in AC circuit will be V equal magnitude ZI. Here all are vectors. KCL will be summation of I vector entering equal summation of I vector leaving. So while you are applying KCL, you have to apply KCL using the magnitude and angle, because the current is a function of time and you are applying KCL at each time. So the current entering at this time equal to the current leaving at the same time, which means we have to do it as vectors, magnitude and angles. And also for KVL, we will write that summation V vector around loop is 0. Today's topic is very interesting and very important to understand what will be happening inside our motors and generators is power in AC circuit. This will be the topic for today's lecture, so I hope by the end of this lecture you will understand physically what is the meaning of power in AC circuits and how we can deal with power in AC circuits. So I will start by explaining some concepts, then we will make these concepts more clear by doing the mathematical or the math proof for what we will conclude from explaining the basic concepts. And we will do a lot of explanation here, and at the end I will give you a summary. So I will give you the whole AC circuit in a nutshell, so just few equations and few steps to deal with any AC circuits from here to graduation, or even when you work in real life in applications. So let's start by, so the topic for this lecture is power in AC circuits. So this will be the topic for the whole lecture, is how we can calculate power in AC circuits. So in AC circuits, the difference between AC circuit and DC circuit is the variability of your source. In DC circuit, your source is constant. It's a DC. So at any time, your voltage is constant. At any time, your current is constant. So when you calculate the power, which is VI, the power is constant. So you are transferring power at a constant rate. You are transferring energy at constant rate. So everything is constant. So calculating power is VI. But in AC circuits, your voltage is a sine wave. And your current is a sine wave. So your power will be a wave. So the power is not constant. So in DC, you will have a voltage that look like this. Here is the time, here is the voltage versus time, and the voltage will be a constant value. Say the voltage is 10 volt, for example. And you will deal with current, and the current I of t will be also constant versus time. Say the current is 2 ampere. So to get the power as function of time, P of t, just you will multiply V by I, so the power will be a constant value as 20 watt. And because the power is constant, its average equal to its maximum equal to its value at any time. So the power at any time t equal to the average power equal to the maximum power, because it's a single value. In our example, it is 20 watt. So here you don't have to specify anything about the power. It's constant and it's 20 watt. So if I'm asking you what is the power in DC circuit, you can say it's 20 watt. That's it. But if we go to AC and you start to look at the voltage versus time, the voltage is a sine wave. So I will try my best to improve my handwriting. So here is the voltage is a sine wave. And if you look at the current as function of time, it's also sine wave. But what is the difference between the wave for the voltage and the wave for the current? That the wave for the current will be shifted with an angle. This angle can be positive and negative. So there is phase shift. And it is from the same frequency. So we said this, the frequency in our circuits is the same. The frequency in North America is the same. So if you have two sine waves, they have the same frequency. What will be the difference between the two waves is when the wave will start. So what is the shift? And what is its peak? What is the maximum it has? So the current will be shifted and the current will have a different maximum value, I of t. Now if you multiply these two together to get the power as function of time, so here you have positive multiplied by negative, you will have a negative power. Here you have positive multiplied by positive, you will have a positive power. So the power also, P of t, will be a wave. So the power P of t is not constant. And this is the power in AC circuits. And this is a huge disadvantage of AC circuits. And this is where Tesla was smart. This is why Tesla was the most brilliant engineer ever. So he solved this issue by using three-phase. In this course, or in this chapter, we will not touch three-phase. We will just cover three-phase. But I will give you an idea what a three-phase is. But the problem was with AC circuit that the power you have is not constant. The power is changing with time. So if this motor or this power is the power to run a motor, so your motor will have a variable power, which means variable torque. And if the motor has variable torque, it will have vibration. So the motor will vibrate and will make noise, which is not good. So And this is the big difference between DC and AC. In DC, you take a smooth, pure, constant power. In AC, you take an oscillating power. Okay? So this is the big difference between AC and DC. So first, I need you to have this in mind, that the power in AC circuits is not constant. It is variable with time. And you can see here some interesting part. And you can see here this part here. So this part here, the first part, it is negative, which means your power is negative. And I'm assuming load notation here. This means you are giving power back. Or your power is positive, so you are consuming power. So here's the power between the source and the load is interactive power. Here the power has only one direction. It's always positive. That's why it's a DC, unidirectional. The power goes from the source to the load. That's it. But for AC, no, the power goes back and forth. So the source will give the load power, the load will take some of this power and return another amount of the power, and so on. If this load is a passive element like R, L, or C, on average it will take power because it's a passive, it's not generating power. So if you take the power coming into the load compared to the power returned from the load, the power coming into the load will be higher because it's a passive element. But if your element is an active element, it's a generator, in this case it can take power less than what it gives. It gives back to the source, and in this case we call it active load. But we don't have active loads, just we will consider passive loads R, L, and C. I hope this point is clear. Okay, so let's move forward. So again, before going into maths, before going into proofs, just let's understand what is the power is. Okay, now let's take the three elements we have. So the first element we have is a resistance. Okay, so the resistance has only one law, which is Ohm. So what is this equation, or this law is telling us? That V of t equals R I of t. So the relation between the voltage and the current is the resistance, which means it's a linear equation. So when I is 0, V is 0. When I is max, V is max. So if we need to sketch V and I versus time here, so if we need to sketch V, so let's say this is V of t and this is time. If we need now to sketch I, when the voltage is 0, I is 0. When the voltage is maximum, I is maximum. When the voltage is 0, I is 0. When the voltage is maximum, I is maximum, and so on. So this is the current. The difference between the voltage and the current is the ratio between the two magnitudes. And the ratio between the magnitude of the voltage, let's write this is I of t. The difference between this magnitude and this magnitude, the ratio is simply R. And the angle of R is 0, that's why there is no shift between V and I. So the impedance Z of a resistance is R with an angle 0. This R is giving you the ratio between the voltage magnitude and the current magnitude. And this angle here will give you the shift between the two waves. So the impedance, as we said, it has two pieces of information. What is the relation between magnitudes? And what is the relation between phase shift or angles? And as you can see here, the resistance has 0 angle difference between V and I. And you can see here that they start together and end together. Why this happens? Why for a resistance no shift between V and I? So think about a resistance like the iron you have at your home, the ironing. So if you look at the iron, or if you look at the incandescent lamps, it's simply a filament. Okay, so if you look at the incandescent lamp, this is an example of a resistance. So what is this lamp is doing? It will take the electrical energy and convert it to heat, which will glue, and you will have light. Or if you have a heater, or if you have an iron, it will take the electrical energy and convert it to heat, and this heat is dissipated, you lose it. So this element doesn't have any way to store energy. It will take the energy, convert it to heat, and lose it. So it will never store energy. It's not an energy storage element. So the resistance is not an energy storage element. It will lose every single energy it will get. That's why there is no shift between V and I. Why there is no shift between V and I? So when I is positive here, V is also positive. So when you multiply V and I, you will get a positive or consumed power or consumed energy. When the voltage reverse and become negative, at the same instant, the current will reverse. Why? So the production will be still positive. You still consume energy. This element physically cannot regenerate energy. It cannot store energy. So we said the passive element on average will take energy. So the passive energy element like RLC will take energy and return energy. And the energy taken is more than the energy returned. This is conservation of energy because it's a passive. For a resistance, it doesn't have a storage capability. So it will take what it will consume. Okay, so it will not return anything. Now, if you multiply VI, you will see that you have a wave like this, P of T. And you can see that the power function here, you can see that the power function here is always positive. It's always consumed. So the resistance will take power and it will always take power. As you can see, the power is not constant, okay? As you can see that the power is increasing. You will see that the power is increasing. It reaches a peak, then it goes down to zero, then it increases again, goes to peak, but it's always positive. If you think about a heater, it's not an issue. If you take power, then the power is variable. At the end, you will see the average temperature. The thermal time constant is so high, you will not see any oscillation in the thermal power constant or in the thermal application. So this is totally fine for heaters. This is totally fine for the iron you have at your home. This is totally fine for the light bulb. Okay? If the light bulb here, it's glowing, is it changing with 60 hertz, your eye will not catch the variability. You will not see this variability because your eye will catch any frequency below 40, I think. So if the frequency is 60, you will not see this. But what if the frequency is 120? It's better for my eye. That's why the high frequency lamps are more expensive, because it has better lighting, better appearance. Okay? Why? Because it's a single phase AC, so the power is variable. So actually the glowing is changing with time. Now let's take the second element we have. Okay, so this is for the resistance. So we can say for the resistance that the power is always positive, the power is variable, and the power has an average. What is the meaning of the power has an average? You can find an average for this waveform. This is the average. The average is not zero. When the average will be zero, if your power has positive part, negative part, and the positive area equal to the negative area, it will sum to zero. And if the power has an average zero, your average energy will be zero. You will take power, return the same exact amount of the power, so on average you're doing nothing. So you will take energy from the source, store it, and return the same amount of energy. This is not the case for the resistance. The resistance will take energy, then it will take energy, then it will take energy, then it will take energy. So it keeps consuming energy. So on average, it has an average power. We will see later on how this average is calculated, and we will do the proof for this. Now, let's see the inductance L. So the inductance, so we started by resistance. So 1 is resistance, 2 is inductance. For inductance, the relation between V and I is not Ohm's law. The relation between V and I is V of t equals L di by dt. It's a first order differential equation. So if we say that the current is a sine wave, so when you take the derivative, the voltage will be a cos wave. Okay? So let's assume that the current is a sine wave, so the voltage is a cos wave. And let's sketch what will be the voltage and current and what will be the power. So here the voltage will be a cos wave, so the voltage will start as peak, then the voltage will go to 0, then the voltage will be peak again, then it will go to 0, and so on. So the voltage is a cos wave. Start at time 0, it's a peak, so this is V of t. If we need to sketch the current as function of time, the current will be a sine wave. So the current will start at 0, and here it will be peak, and here it will be 0, and here it will be peak again, but let's make its peak a little bit smaller, and here will be peak again, and here will be 0, and so on. And this is the current I of t. And this is a general relation between V and I, that V equals L, the derivative by I of t. We will prove this physically again in magnetic circuits, even we will get how they came up with V equal L di by dt. Why L di by dt, and what is this L physically, okay? So we will do this in magnetics. Now, if we multiply V and I to get the power, you can see here that the voltage is positive and the current is positive. So here the power will be positive. If you go here up to this point, the current is positive while the voltage is negative. So the power will be negative. If we go here, the power is, or the voltage is negative, the current is negative, so the power is positive. And here, it's a positive negative, so it's a negative. So as you can see that the power is reversing its polarity. So the power will be consumed, then supplied, then consumed, then supplied, then consumed, then supplied. It's different from the resistance. The resistance, the power is always positive. But the power for an inductance, it's changing. So the inductance will store energy, supply energy, store energy, supply energy. Why the inductance will do this? Because the inductance is based on magnetic phenomena. So the inductor is taking energy, converting this energy into magnetic field, is storing this magnetic field into what is called a core, a magnetic core. Then it can release this energy again from the magnetic core. So the inductance is acting like an energy tank. You can store an energy into inductance in the form of magnetic energy or magnetic field. So the inductance will take the energy, store it as magnetic, then it will take the magnetic and store it again, or supply it again. So the inductance will take electrical energy from the source, convert it to magnetic energy, store the magnetic energy, then it will take the magnetic energy back, convert it to electrical, give it back to the source. And if it is ideal inductor, the energy stored equal to the energy supplied. So the average will be 0, assuming it's an ideal inductor or pure inductor. That's why you can see all these parts are equal. So the wave is divided into 4 equal durations. That's why the shift is 90 degrees. Exactly 90 degrees. That's why the shift between V and the I is exactly 90 degrees. 90 degrees. So the average energy is 0. So the energy you charge equal to the energy you discharge. This is what is called pure inductance or ideal inductance. What if the inductance is not ideal? We will see this. It will be represented as R and L. R is a non-ideal part. Okay, will be later on. But as you can see here, sorry. So as you can see here, that the average power will be 0, or the average energy will be zero. So here you charge, here you discharge, here you charge, here you discharge. And you are multiplying sine by cos, which will give you sine double the frequency. So if you multiply VI, so V is cos, I is sine. When you multiply cos and sine, it will be, if you convert it to sine, it will be sine double the frequency, double the angle. So it will be a sine wave at the end. So it will be a sine wave. So here it will be 0. Here 0 by peak, it will be 0. It will be 0. It will be 0. It will be 0. And here it's positive. So then it's negative, then positive, then negative. So the power will be a wave. So the power will be a sine wave. Let's make this more clear. So the power will be a sine wave here it's positive, here it's positive, here it's negative, here it's negative. So the average power is 0, which means that this area here is equal to this area, and this area equal to this area. The idea here, so this is P of t, and this is time. So how many charge discharge you did here per cycle? So the source did just one cycle. So up to this point, your source did one cycle, but your power did 2 cycles. So you did a charge, discharge, a charge, discharge. So here you have 2 cycles of power, but here you have 1 cycle of source, which means that the frequency of the power change is double the frequency of the source change. And we will do this by mass. We will do the proof for this. But now we have another concept for the power. We cannot treat this power here for R as this power here for inductance. We cannot treat it the same. The power of the resistance is one way. It's converted to heat. It's converted to non-electrical form. So this power is dissipated. So this power is productive. The power inside the resistance is productive. But the power inside the inductance, it's not productive. It's an interactive power. The source gives the load the power, the load takes the power, then it gives it back to the source. What is the benefit? Okay, we will know what is the benefit later on. But on average, you did nothing. You are going forward 2 meters, then you are going backward 2 meters. So you're back to the same point. So we need to give a definition for this interactive power. Okay? Now let's take the third and last element. And the third and last element is C, or capacitor. So for capacitors, we have the equation that I equals to C dV of t by dt. So if the voltage is cos, to keep the same reference as inductance, so I will keep that the source is cos function. Okay, so if the source is or the voltage is cos, the current will be the derivative of a cos function, which is minus a sine function. So if I need to sketch the relation between V and I, so how we will do this? Okay, so I will do V as cos. So I will start here peak, then 0, then peak, then 0, then peak, then 0, sorry, peak here, and 0 here. So here is V of t. If I need to sketch I of t, it will be sine, so it will start here as 0, but it's a negative sign, so it will be negative peak here instead of positive peak in the case here, and then it will go to 0, then it will go to positive peak, then it will go to 0, and this will be your current I of t. Now if we multiply V by I to get the power as function of time, we can see here we have positive negative, so it's negative. Here we have negative negative, which is positive. Negative negative means the current is negative, the voltage is negative, so when you multiply them you will get a positive value. Here we have negative positive, so negative. Here we have positive positive, so it's a positive, and then negative. And as you can see, it's a repeated version of the inductance. So it is a changing polarity each quarter waveform. So each pi over 2, you are changing polarity. So it's typically what is the inductance is doing. So the capacitor is doing the same phenomena as the inductor. It stores the energy, but and then returns the same energy back. But the idea here is that the capacitor is storing the energy in the form of electric field, not magnetic field. So it's a different way of storing energy. So the capacitor is acting as an energy storage tank. So it will take the electric energy, convert it into an electric field by accumulating the charge on a positive plate and on a negative plate. So you are building energy, then you will take this energy and supply it back. So the average is 0. But the difference between the inductance and the capacitance, that the inductance starts positive and the capacitor starts negative. So the power of the inductor with respect to the capacitor, it's opposite. So when the inductor is charging, the capacitor is discharging. Okay? So if we write here, so this will be discharge, this will be charge, this will be discharge, this will be a charge, this will be discharge. So when the inductor here is charging, the capacitor is discharging. So they are doing the opposite. So when the inductor takes energy from the source, the capacitor is giving energy to the source. That's why if you have an inductor and you added a capacitor in parallel, they will counterbalance each other. That's why if one is positive, the other is negative. Because one is charging when the other one is discharging. That's why they are opposite. L and C as power, in terms of power, they are opposite, they are negative. But still, as a behavior, the power of the capacitor is the same behavior as the power in the inductor. This power is going back and forth between the source and the load, and it has no average. And when you multiply I, which is negative sign, by cos, you will have sine cos, which can be converted to sine double the value or double the frequency. So it will be a sine wave, but this sine wave is reverse. So this is the power for a capacitor. It's a sine wave, but it starts negative. And as you can see here, per one cycle of the source, you have 2 cycles. So you have 2 cycles of power. Let's make it a little bit neat. So you have 2 cycles of power per one cycle of source. So each 2 cycles of power, or each one cycle of source voltage, for one cycle of source voltage, you will do 2 charge and 2 discharge. So per one cycle of the source voltage, you do 2 charge and do 2 discharge. Or the frequency of the power is double the frequency of the source. And if you can see here that the power here is positive and the power here is negative, with an average equal to 0, because you divided the cycle into 4 equal pieces, and in each period or in each piece you are charging or discharging. And comparing L and C, they have the same behavior, oscillating power with double the frequency, with 0 average, positive and negative, so you charge and discharge. But the inductor and the capacitor are opposite. When the inductor charge, the capacitor discharge, and when the capacitor charge, the inductor is discharging. So now we compared between the power in DC, the power in AC, the power in AC for a resistance, the power in AC for an inductance, the power in AC for a capacitance. Okay, so these are the basic ideas for what is happening physically. I will break the lecture here. The next part of the lecture will be doing a mathematical proof for what is going on. Okay, so I will stop this lecture.